The following video was taken from Ace Organic Chem Elite, full of movies, videos, flashcards, a test bank, and much, much more. Plans start at less than $20. Sign up today and get 2 free ebooks with your subscription. Cancel anytime, money back guarantee if not completely satisfied, and you keep the ebooks. Just click on the link in the video notes. And now, on to our video. In this video, we're going to talk about the Baeyer-Villager reaction, which is sometimes called the Baeyer-Villager oxidation or the Baeyer-Villager rearrangement. So let's start with an easy example of it. Here I have, what is this here? This is 3-pentanone. All right, so this is a ketone, and I'm going to give you a little hint ahead of time. It's a symmetric ketone, and that's going to help us out in this case. When you're doing the Baeyer-Villager reaction, we need a peroxy acid, so we're going to start with the easiest one. We'll just start with peroxide. And to spice up the reaction a little bit, you can put in this Lewis acid. And when you do that, what happens is kind of cool. You add an oxygen to the end. You insert an oxygen next to your carbonyl. So you can see we've inserted this oxygen. There was 2 carbons, so there's an ethyl group on one side and an ethyl group on the other. There's still both of those. There's still an ethyl group. Started with an ethyl group here and an ethyl group here. We finished with an ethyl group here and an ethyl group here. But now instead of being an ethyl group on either side of the ketone, we've got one is the carbonyl side over here and then an ethyl ester instead over here. So what we've done is an oxidation. We've taken a ketone and turned it into an ester. Baeyer-Villager is a really nice reaction. Let me tell you, your professors love the Baeyer-Villager reaction. Let's check out another substrate that we can do this on. What about cyclohexanone? So if we were to take cyclohexanone and subject it to Baeyer-Villager conditions, and this time I'm going to use a different oxidizing agent. It's still a peroxy acid, but it's one that you're used to seeing for epoxide formation, MCPBA. And when you subject that, remember we're going to add in an oxygen. That's exactly what we do. So we go from a 6-membered ring to a 7-membered ring. One of those members of that ring is an oxygen. So there's still 6 carbons in the ring, 1 oxygen. So we've expanded the ring. We've gone from a 6-membered ring to a 7-membered ring, but we've kept our carbons the same. So this takes a cyclic ketone and turns it into a lactone, which is a cyclic ester. Same reaction, same stuff. Cyclic ketone to cyclic ester, lactone. One more example here before we start talking about mechanism. Now we're going to get a little trickier. What would happen if this was not a symmetric ketone? Which side will the ester end up on? So let's look at this now. We're going to take our conditions. We're going to take the easy conditions here. Asymmetric ketone, what happens and where does it go? What ends up happening, we can take our ketone there. Excuse me. There we are. We are going to add that oxygen to the more substituted side. So now we have a propyl ether. Look back here, 3 carbons on the right, still 3 carbons on the right. The oxygen went to the more substituted side, and that's almost exclusively what happens. Why? Let's check out this reaction here for a second. So first of all, I'm going to start with, we'll get rid of that. So we have the ketone that we looked at in the last reaction, and we're going to use a peroxy acid with it, and that peroxy acid is, this is the peroxy acid of acetic acid. So we'll make that small and we'll put that up there. That's our reaction. So when we have these two guys in solution, what happens is, and if we use the ease method, let's start labeling some things here. I see that the ketone is going to be the electrophile. Put a big E there. And I'll give you a hint. This end oxygen is really nucleophilic, right? Because it's a peroxy acid, which means, remember, we can always lose that hydrogen, put a negative charge there. Negative charge there. So this is our nucleophilic oxygen. That's what's going to do the attacking. So we'll write in nucleophile there so we know what's going on. I don't see any acid or bases, and I don't see any steric conditions. So now let's just move some electrons. All right, we're going to attack that. Let me redraw that. There we are. Boom. We're going to attack that carbonyl right at the base. Get this E and the NU out of here to free up some space. Kick up the electrons to the top oxygen. When we do that, here is our intermediate. And we need to stay electrically neutral. So remember, we have H plus floating around. That's this hydrogen right there. This is our intermediate. Now, we have a lone pair up here that can come down and reform that carbonyl. It will do that. But if to do that, when we reform the double bond right here, we need to break a bond, one of these three bonds. If we break the bond that we just formed, now it's a reversible reaction. That reaction is just going to go in the other direction. And that could happen. I mean, this is reversible. But the permanent reaction and the permanent change would be if, and this is why it's called the rearrangement. This bond right here on the more substituted side, the bond itself is going to break, attack that oxygen, and kick off a carboxylic acid. So what you end up with then is what we're looking at, what we've been talking about here as the product. Let's draw that there. There we are. Right, so that is the product. And what happens is, remember, we're reforming the carbonyl and then we break that bond right there. And this group, the more substituted group, comes along and attacks the oxygen, which kicks off a carboxylic acid as a byproduct. So the carboxylic acid, which is acetic acid in this case, is our byproduct. So we'll draw that here just for clarity's sake. And then, of course, we have our hydrogen there that comes back into the picture and forms and quenches that to form the carboxylic acid. We formed our ester. Everything is looking good. So that's really the mechanism. And it's this intermediate, and I'll draw this line back in here so that nobody's confused. It's that intermediate that rearranges. So to talk about, and we call this a migration, and to talk about that migration, tertiary groups will migrate faster than secondary groups, which will migrate faster than primary groups. That is the order. So if you have a choice, it's that more substituted side is what's going to come over. Now, let's look at one other example here. Well, two other examples, I guess. So here's our example. What would happen if we did a Baeyer-Villager reaction on an aldehyde? Where would that go? Well, what we didn't tell you, so we talked about migratory propensity. And we said that primaries go faster than secondaries, which go faster than primaries. What we didn't tell you is that hydrogens move the fastest of all of those, because it's nice and easy to detach one of those. It's easier to break a carbon-hydrogen bond than it is to break a carbon-carbon bond. So what happens, same mechanism, same everything, except instead of this side migrating, the hydrogen just migrates. And when the hydrogen migrates, you get out of carboxylic acid. So what this has done, in essence, is all we've done is just do an oxidation on this. And, of course, the Baeyer-Villager reaction itself is an oxidation. You're going from a ketone to an ester. That's an oxidation. This is the easy oxidation, going from an aldehyde to a carboxylic acid. So hydrogens are going to migrate first and foremost. And if you don't have a hydrogen, if it's a true ketone and not an aldehyde, it goes by how substituted you are. Remember, the more substituted side is going to get the oxygen in the Baeyer-Villager reaction. Don't forget that. That's the most important thing. One other thing I'd like to discuss before we wrap up this video. We've talked about that if you take cyclic ketones, react them Baeyer-Villager style, and I'm going to scroll down a little to give us some room on this. Remember, you're going to, quote, expand the ring. We're going to go from a 5-membered ring to a 6-membered ring. And that's what you get out of it. But this is kind of cool now. Where can I go with that lactone? What can I do? Well, you can subject that to water. And actually, we'll call this light acid. If you subject it to a light aqueous acid, you're going to protonate and then open up this ring. And when you open up the ring, you get something kind of cool. I'm going to count my carbons to make sure I did this properly. I think I did. We're going to open this ring up. We're going to hydrolyze the ester, which you know you can do. And what you get out is a hydroxy carboxylic acid. So let's count our carbons to make sure we did this correctly. There are 5 carbons in this ring. 1, 2, 3, 4, 5. Make sure we have 5 carbons in our final product here. 1, 2, 3, 4, 5. We do. Great. So what we have here is we've opened this up, and you could call this a what? Alpha, beta, gamma, delta. So this would be a delta hydroxy, right? Because the hydroxyl group's on the delta position. A delta hydroxy carboxylic acid. Awesome way to form these things. If you see this in a synthesis problem, it came from a cyclic ester or a lactone. And we know that this is reversible. Because if you do it properly under the proper conditions, that can come back around and attack there, and you can reclose this ring. So this goes back and forth. But a nice way to form these hydroxycarboxylic acids. There's not a real good way to put a hydroxyl group way on the end of this ring. This is a way to do it. Hopefully that was helpful. And go ahead and move on to the next video now.